something, 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 something.
Hello, hello. Thank you for joining us at United Astronomy Clubs of New Jersey. Uh, our presentation tonight is You Can Almost Touch the Stars by Tom Field from Sky and Telescope magazine. He's been an editor at Sky and Telescope for the past 7 years. He is the author of the RSpec software, which received the Sky and Telescope Hot Product Award in the 2011. Tom is a popular speaker who has spoken to hundreds of clubs via the web and in person at many conferences, including NEAF, the NEAF Imaging Conference, the RAC Winter Star Party, the Advanced Imaging Conference, and others. And with that, I will hand this over to Tom. Thank you for joining us.
You're welcome, Kim, and thank Christopher and the others who make all these things happen behind the scenes. There's a lot of logistics and pre-planning and testing and emails that go back and forth, and I appreciate that. They help keep our clubs active the way they are. And I love your club logo. I speak to a lot of clubs. I always like to put the logo up here. That's a great logo. I like it. Very professional. The good news is if you're watching this live, then after my talk, you'll be able to ask questions through the moderator, and they'll be relayed to me, and I can answer them. So I hope you'll hang around for that. I'm going to speak for about 50 minutes on how we know so much about the stars and how we can almost touch the stars. So with that, let's get started. We've got a lot to cover. So how is it that we've managed to discover so much about the universe? You know, we haven't really even left home, have we? We've been capturing images for more than a century, and we get certainly a lot of information from that. And occasionally, during eclipses, we can see that one object is in front of the other. And if we wait a while, we can see that things are changing. That's a fourth dimension time. You can see, for example, in the upper right-hand corner, that stars is going on and off. There are others in there also. If we spread the colors out, and by the way, this is an image from Lake George, just north of many of you in New Jersey, taken this spring. When the colors are spread out, we see this beautiful rainbow with all these gaps. And those gaps tell us an enormous amount about stars, our star as well as other stars. So I won't read these bullets, but you'll be seeing over the next half an hour or 45 minutes some examples that show how you, with almost whatever equipment you have, can study the spectra of the stars and learn how it is that professionals do this kind of thing. Now, if you're an armchair astronomer, or maybe you don't do any imaging today, that's okay, because still what I'm going to talk about today will help you appreciate and understand other things that you read, whether it's magazine articles or web-based, and also understand a little bit more about the things that you observe and think about in the field. So let's do just a little bit of science to get people up to a common level here, and that is Sir Isaac Newton discovered that you can bounce light through a prism and split it into its component colors. And you can even bounce that light off a finely lined surface like the DVD you see there. Before I go on to the next slide, you can pass it through a piece of glass that has fine lines cut into it. And we'll look at that diffraction grating in a moment. So Bunsen invented his Bunsen burner here to burn samples, put the light through a prism, and look at the result. And he was a real pyromaniac. He burned everything. And the good news is he kept a catalog. And that catalog of every spectrum he saw, and we'll show some examples of that in a moment, has really served us in the field of astronomy over the next century and a half, and or a little more. We'll see how that catalog works in just a moment. This guy, Kirchhoff, was a contemporary colleague of his. We're not going to spend a lot of time talking about him, but I wanted to show just one example on this page, and that is, notice that this spectrum, it's a rainbow. It's like what we'd expect out of a prism, and it has gaps in it. But sometimes we get a spectrum that's all dark with bright lines called emission lines. Now, which one you get depends on things Kirchhoff spoke about, but we won't tonight. You can Google his name to learn a little bit more. Temperature of the gases involved and things like that. But the really cool thing is that whether there are gaps or there are emission lines, they're in the same position. And we'll look at what these are and why they happen in examples over the next half hour or so. So these gaps, whether they're emission lines or absorption lines, are like fingerprints. So for example, hydrogen, if you, or like Bunsen burned hydrogen and put the light through a prism, you would see a really strong line here that doesn't exist here in helium. This would be the helium you might, for example, you go to a flower shop and you get a balloon that, you know, is on the end of a string. It's filled with helium. It doesn't have that line. In fact, hydrogen is so common that, and so frequently used by scientists, that it's good to be able to refer to the hydrogen lines with this generic term, Balmer lines or Balmer series, it's called. And there's one, in fact, they're actually given names. Hydrogen alpha is that one in red, and that beta, that's, I guess, that's robin egg blue, okay? And then there's a hydrogen gamma. So we'll talk about and see examples of those lines as we go forward. A few years ago, I created this poster, mostly for educators who buy it from us. Some amateurs do also. The reason I have it here isn't to dive into each of these examples. Neither of us, none of you or me would survive that. But I wanted to show you just a close-up of the hydrogen here. You can see there's a hydrogen alpha. There in what the robin egg blue, there's the beta and the gamma, and then the lines getting closer together. And look, compare that to helium. You can see the lines are very different. This is the magic key to our understanding of stars, is these fingerprints. So we don't have to burn light anymore, burn objects, gas, or matter, or whatever, materials, solids, that's the word I was looking for. Now we can actually use a gas tube. They're like a fluorescent tube or a neon lamp. And in fact, I'm going to pull up on the screen here. Let me get it up here. There. Give me just a second. There it is. And this is a live video. Diva that I am. Look, that really is me. And I'm going to take this tube here that I was waving around in front of the other camera. You can see, maybe you can see hydrogen written on it. And I'm going to plug it into this power supply with it off and turn it on. Now, what we're using here, by the way, is a little camera that we created. I'm showing it on the other video, my live video, and I can show it to you here. It's a little camera that we created for physics, chemistry, and astronomy teachers for classroom teaching, and it's really effective at that. This is the gas tube, and that's the spectrum, the same spectrum that Bunsen saw. There's our hydrogen alpha, there's our hydrogen beta in the robin egg blue, and the other colors there dimming out into the UV. So this is a spectrum that we can look at in stars and compare and see, well, does a star look like that? And that's what we're going to talk about tonight. So let me dump that screen and come back over here and come back to here. So far, everybody I've talked about have been old white men. Let's look at some others. There's really some astonishing people that have made enormous contributions. So first of all, Annie Jump Cannon and her team of women, who were called the computers more than a century ago, were prohibited from accessing the telescopes at Harvard because of their gender. So what they ended up doing was studying the glass film plates of spectra captured on those telescopes. And they were really good at it. They classified hundreds of thousands of stars. So by quantity measure, they were good at it. But even more important, with their exposure to all that data and their deep insight and knowledge in the field that they gained over those years, they were able to come up with a star classification scheme that actually worked, unlike the predecessors. It helped us understand the lifestyle of a star. Yeah, the life cycle of a star. So over here, Priyamvada Nataraja is at Yale. She studies black holes and the gravitational lensing around those. Nancy Grace Roman was the first astronomer at NASA. She got her PhD in the late 1940s. She was a big proponent of the Hubble Space Telescope that you see there, thank goodness, and what a great instrument that's been. And Elisa Quintana studies exoplanets, and she discovered some around some red giants, among other things. And finally, Jedediah Eisler's at Dartmouth, and she studies hyperactive black holes. This is just a handful of the people I found this summer when I was putting together this slide. It was a fantastic search. I really enjoyed discovering just how many people there are out there who we haven't heard of who've done fantastic work. We've made a little progress in that direction. There's a lot more that we can make. So tonight I'm going to talk about mostly this little grating right here called a star analyzer grating. Now, this grating, you know, I used to put up a slide that listed all the key points I wanted to make so people knew what they were in for. But nobody wants to read slides. So I've changed my tune now, so to speak, and now I have this. This means this used to be on that bulleted slide you don't want to read, and nor did I really want to show. But this means key point, basically. It's a ding moment. The ding moment here is that there's this myth that I think a lot of us, I know I had 15 years ago, that to do this kind of science is expensive. This grading is only $200. So that myth is gone. It's not expensive to do this. Not only isn't it expensive, but the other myth is, well, I'm going to have to become a do-it-yourselfer and build this complex device, use all these lasers and machine shops. It's really easy. Here's some examples. So that ding moment, that myth is gone. It's not hard to use a grating. Basically, I've just got some examples for us here. Here's a grating on a DSLR. This is a little thread adapter that we actually machine here that lets you thread it onto the lens cap threads of a DSLR. It could be a fixed camera, cooled, uncooled. It could be a video camera like this ZWO camera. This is a color camera. You can use color. It's not quite as sensitive, and it's not scientifically, it's a little compromised, but works fine. Why go out and buy an expensive camera if you've got a color camera until you find some reason that you need a mono camera or an expensive cooled camera? And this example here just shows that we could put a grating inside a filter wheel. So there's lots of ways to mount a grating. You can even put a DSLR piggybacked on a telescope so you can multitask, as if we don't multitask enough already these days. Okay, so now we've got all that history, theory, equipment out of the way. What can we actually do? Well, we take a grating and we put it in the light path in our setup, and we get a spectrum here. Some of the starlight just goes straight through and becomes a star on our sensor, and then we get this beautiful rainbow. This next example is really fantastic. These are separate spectra captured of different stars at different times by Torsten Hansen. You can see up here with an 8-inch Newtonian and an imaging source video camera. So, you know, a few minutes ago, I mentioned that one of the things that we learned from spectra, this is one of those bulleted points, was that we could tell star temperatures. Well, these stars are in temperature order, starting with the really hot B stars and then the A's and the F's down here to the M and K stars. Look at the differences in spectra. So clearly there is a temperature difference from these spectra. And this is a ding moment too, because I think a lot of us think that, you know, okay, the grating's inexpensive. I don't need to buy a new camera, but I'm going to have to take these really long exposures. I'm going to have to be on a mountaintop. I'm going to have to be like the cream of the crop imager. Of imaging source video camera. So some of these images, all these images are less than a quarter second long. So it's not that hard to capture spectra. So I want to show two examples here that help us understand the stars. First, down here, we see some lines. In fact, that's sort of like a forest, isn't it, of lines? It's called a band. On these cooler type M stars, the stars are cool enough that not only hydrogen and helium and simple elements can exist, but more complex elements don't get immediately incinerated. And this band is an indication of a more complex molecule. In this case, it's a molecule called titanium oxide. Now, before you space out like I did the first time I heard that word, I have a confession to make, amongst others I'll make tonight. I don't know anything about titanium oxide. Why? I don't care to. There's plenty to know. You don't have to, there's no quiz. You don't have to dig into everything. And I think what spectroscopy has done for me is the more that I've learned of the simple science, the more the foundation I've had for my visual observing, for my reading of the magazines, for my web surfing. So you learn as you care to. So I'm going to sound like I know what I'm talking about tonight, but honestly, I'm like a really broad river that's really shallow. So The other thing I wanted to look at here with you for just a moment is that region. That's well, that's our robin egg blue area, right? Where that hydrogen bomber feature would be. And that's what these lines, these absorption features are. Notice that one of them is much more prominent, right? This one. So this is a type A star like Vega, for example. I didn't know the star types that well when I started all this, but once you start looking at spectra, they begin to stick and sink in. So let's review just for a moment how spectra happen. You may be familiar with the Bohr model of the atom, which has these orbits, right, that electrons are sitting in and go around in. And they jump sometimes between levels. And when they jump between level 2 and level 4, that's when you get this gap, this absorption feature. If they're dropping down, then this becomes a bright line instead of an absorption feature. So why are these lines so much dimmer than this line? Well, these hot stars are so hot that when an electron's getting pumped up, it doesn't, a lot of them don't stop at this level, and they keep going to 5 and up and out maybe. So there aren't as many electrons making that transition between 2 and 4. And down here below, why are these dimmer? In fact, they don't even exist, this line here, because a lot of the electrons don't even get pumped up to level 4 because those stars are so cool. So the existence and the strength of this line helps us determine the star temperature. So that's about the deepest science we're going to talk tonight, I think. In the Q&A, let me know if you think anything else I talked about was a little more of a challenge. I'd be curious. I've never asked that question before. So you see that, I'm trying not to drop my grading here as I talk. So you see that, and let me also tell Outlook again to leave my cursor visible. You see this area right here? Maybe you can see there's a little dimming here. Well, suppose I got time on a professional telescope. I did some spectroscopy. I wrote it up. I submitted what I found. And in that submission for that paper's publication, I said, there was a little dimming in the robin egg blue. That paper's not going to get published, right? Because that's not science. That's qualitative. To do science, we have to be quantitative. And to do that, we just graph the intensity of this region. So this graph, this axis is brightness or intensity. So this star is really bright, but it's narrow, right? So this peak is really high, but it's not very wide. Whereas this thing is really wide, and on the ends it's dim, but in the center it's bright. So this is dim, brighter, 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 dimmer, 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 dimmer. But check this out. Look at that dip in the intensity. We can barely see it there, but it's so clear here. Now we're doing science. Now we can measure where that dip is, what's the full width half maximum, how's it compared to the same star tomorrow night or a different star tonight or a different telescope. This is fun. So how do we get this graph? That's a really good question. So my story is again, in about 2009, I wanted to do some spectroscopy. I got a grading, like our star analyzer grading. I put it on my C8 one night, one Saturday night in August. I went outside, right outside the window here. And, you know, I set my telescope up. I was using, I had it here. Oh, here it is, actually. I was cleaning my office. I don't normally have that. This is a Logitech webcam. You can still see the adhesive from the duct tape because I was, duct taping it to the barrel of an eyepiece that I'd taken apart. I captured some video of Vega. At midnight, I came in. I had a sore neck. I had grass stains on the blue jeans that I was wearing. It's Vega in August. What do you expect, right? The next morning, I wanted to create this graph so I could do some science. I downloaded some of the freeware that was out there. The first one I tried to install, it wouldn't even install. There was some sort of DLL hell, if you know what that is. You don't want to know what it is if you don't. And the other software, in fact, both were in French. It's really frustrating when a piece of software, not only does it pop up an error message that's in French, but then it crashes. And both these programs were in French, and they just weren't up to the usability level that we've become accustomed to. So what did I do? I gave up. I told my wife, I'm so frustrated. This is a hobby. I'm supposed to be having fun. And I literally, you have to say it twice these days. I literally put the grading in my drawer. I gave up. but I really, over the next couple of weeks, in spare moments, I'd be thinking about it. So I said, look, this weekend, I'm going to write a program. I've been programming since the 60s. I'm going to write a program, and not since I turned 60, from the 1960s. So I'm going to write a program to extract this graph from the sensor image. And I did. Sunday it was done. And now 10 or 15,000 hours later, it's almost done. My wife keeps saying, would you finish the software so we could eat dinner at the same time every night? She used to say that. It's done now. I hadn't intended to create a program to sell for people to use, but it became popular. So I think one of the obstacles, in fact, this is a ding moment. One of the obstacles to getting started new in something like this is, oh, I'm going to have to learn a new program, a new piece of software. That's a real obstacle, and I faced it too, as you heard a moment ago. I know better than to show you a video or to do a walkthrough of my software. You know, when I give live Zoom sessions, when I can see everybody's videos, if I was to do that, I'd start seeing people's heads as they nodded off to sleep. Fortunately, they might be muted, so I wouldn't hear their snoring. But I think it's important enough for me to show you just a couple of clicks in my software so that you see how easy this can be. So there's the software there. I'm using a color image because I think it's more intuitive. There's the star, there's the spectrum, there's a gap there and some gaps there maybe. All we do is bracket it in with these lines, and then over on the right, we get that intensity graph. This could be a FITS image. In this case, it's literally a paused frame in that video from my first night. And I was not a good imager, I assure you of that. I was surprised as anybody is, and most people are surprised the first time they capture a spectra and how easy it really is. First time they capture a spectrum. So this peak here is the star, and this thing is that thing. For example, that dip, that deep dip that's right there, it's that gap, it's that absorption feature. So that's all very well and good, but I bet some of you are thinking, so what? There's dips. What do they mean? I mean, we're not astrophysicists. Remember a few minutes ago, I mentioned that Bunsen created this great catalog. Well, the great grand catalog, grandchild catalog is still being used today. And I've embedded it in the software, some of it. So here's that catalog. I can come down here to the software, and I can say by checking this box, put an overlay on that graph that shows me where the hydrogen bomber lines would be. Those lines that we saw with this, if I don't knock it over, with this gas tube here. So there's our hydrogen alpha, there's our hydrogen beta, there's our hydrogen gamma, and we've got absorption dips in the data here that match all those lines. So we've fairly conclusively shown just now that the dips in my data are the result of the hydrogen in the outer shell of that star. As the starlight leaves, electrons are jumping up and down, absorbing light just at those hydrogen wavelengths. That's really exciting the first time it happens to you. It really is. And it still is to me now, 11 years later or 12 years later. So a couple things I want to show you. First of all, this is, as I mentioned, a paused video. It plays at 2 frames per second. That's the frame rate I recorded. This is from that first night outside with my C8. You can do this with a 4-inch or a 6-inch telescope. I'm going to start play because I'd like you to see what it looks like live under the stars. My seeing was changing, so you can see the star changing and the spectrum changing. Of course, my graph is changing then too. Features are coming and going. In fact, let's look at that. There's that hydrogen alpha feature. See how it comes and goes? It's never really all that stable. Most of us are familiar with the fact that we can stack multiple images to eliminate noise. The software for video has a stacking feature in it. So watch this dip when I turn the stacking on. In the space of 5 or 10 seconds at 2 frames per second, notice how it stabilized, it became relatively smooth, it's not jumping around anymore. That's what stacking can do. So this image here is a huge winner if you're doing outreach, public outreach. It's color, It's moving. People want to know what it is, and it offers a starting place for you to talk a little bit more about the science of astronomy and how we know what the stars are made of. You don't have to be an astrophysicist to understand and explain some of what you're seeing here. So with that, I'm going to leave the software. I'd like you, if you would, in your mind's eye, if you could remember that view, not because it's Vega with its dips, but because it's got these reference lines here from Bunsen's catalog of the hydrogen bomber series. Because in a few minutes, I'm going to show you some research that takes advantage of this data. And I think it would be helpful if you can remember you'd seen it before. So here, for example, is a star party like I mentioned earlier. They're looking at a gas tube, and then they looked at a star. This happens to be in France, but like I said, this is a really captivating view for newcomers. Here's a wide field view. Here's a handful of stars. You can see their spectra here. There's a gap, an absorption feature. Down here, we have another different type star. Its spectrum has these lumps, right? Well, these are emission features, and they're so strong here that they saturated our pixels, and we got a little bit of blooming. In fact, let's look at a Wolf-Rayet star. So I have a confession, the true confession to make here. And that is when Janet Simpson sent me this image, I couldn't remember what a Wolf-Rayet star was. I knew it was a technical term in the field, but I'd read about them maybe like you a half dozen or dozen times over the years, but oftentimes it would just go in one ear and out the other. Well, Wikipedia is our friend, right? Wolf-Rayet stars are late-stage stars. They're massive. They have intense stellar winds, so they're dissipating their outer shell, headed perhaps to being a supernova. And we have emission. We have these bright lines. Let's see what they look like. Look at these peaks. There's carbon, there's carbon, there's carbon. Why would we be seeing carbon in a star if they're made of hydrogen? Now remember that stars fuse hydrogen and helium through a whole process of elements. And in that process, at a certain time, they're fusing carbon. That's why we're seeing carbon here. It's pretty amazing that we can do that with just a DSLR, even with that small aperture. In fact, DSLRs, again, just to show you as an example, with this little adapter on the front and then the grating, if I had another hand, I'd show you the grating in that hole. DSLRs can be very effective with their low aperture on certain types of targets. Well, let's look at another object that's an emission object that has peaks. Here's our beloved Ring Nebula, and there's its spectrum. We've got hydrogen, and we've got some oxygen. That Roman numeral 3 just means it's ionized. Some of the electrons have been pulled up. So most extended objects like this, as opposed to point sources like stars, aren't interesting in a star analyzer. For that, you need a higher end device. You need a device that has a slit like these. Now you'll notice these are an order of magnitude or more expensive. And they're a lot harder to use because now you're basically tracking and acquiring your target on a 20 or 30 micron slit. So really almost nobody starts out with these. It's a big step economically, and also the grading is important. Even after you're doing slit spectroscopy, there's things gratings do, like this low resolution grading, that you can't do with slits. It's a nice gentle learning curve. So let's look at an emission object with a slit device, just so you see what they can do. Let's look at our showpiece M42. We can see there's our hydrogen alpha, and there's our oxygen with that Roman numeral 3, that ionized oxygen. It's certainly an extended object, right? Notice how narrow the peaks are and how little tiny ones we can see. This is what a slit spectrometer can do for us. So my story is, in the early 1990s, I didn't have a telescope. I read about Shoemaker-Levy 9 in the popular press. I decided I wanted to do this stuff so I could see it as it came up in a few months. I went to a Denver Astronomical Society first quarter star party in the city. And I got out of my car, I walked up on the bluff, overlooking the observing field. It's fun to remember when you didn't know something. And in this case, I looked down on that observing field. And what I saw, you know those cannons that they shoot people out of at the circus? That's what I thought I was seeing. And I'm going, WTF, what is this, you know? Of course, they were Dobsonians. What did I know? So I queued up at one of these devices. There was somebody much like some of you watching this today or watching a replay later, or me. They were running the telescope, explaining what we were seeing or what we were going to see. I was all excited. And then I got to the eyepiece, and I was really disappointed. It was a smudge. I'd seen photographs of these kinds of things. This was not that. I was really disappointed. I bet some of you have had a similar experience. But even with that experience, I, and maybe you too, in fact, if you're watching this video, I'll say you too, not maybe, still go back and look at M42. Why would that be? Why would we still look at it if it's just a smudge? Well, first of all, we've got better telescopes. You know, maybe we're at a dark sky site. Also, we've gotten better at averted vision. Right now, we know how to use averted vision to use the more sensitive parts of our eyes to observe dim objects, right? But seriously, the reason we go back, even if it's a smudge, is now we understand what we're looking at. It's the birthplace of stars, a stellar nursery. My point is, and this is really a ding moment, when you understand what you're looking at visually, it becomes that much richer an experience. And you've experienced that in your career in amateur astronomy. Spectroscopy has done that for me. As I've learned some new facts because I've captured spectra, those facts, not only do they help me visually observing, but here's the other thing, another ding moment. And that is, when you own the data, your relationship is completely changed. It's no longer just an image that you turn the page on. Now you study it, you look up things about it, you remember those things, all great side benefits of doing some simple spectroscopy. So here at the top, we have the spectra of Uranus and Neptune. There is a deep absorption line that's that's one of those forests or bands. And we heard earlier that on cool type M stars, they're cool enough that you can have complex molecules. Well, what sort of complex molecules would we see with a video camera, would we see on Neptune and Uranus? Well, what about methane? We're seeing the methane absorption bands on these planets with a backyard spectrum of the star, of a comet. And the New York Times thought it was important enough in this day to publish it. So here's the spectrum here, this beautiful string of gems. We can do it. Heck, if Hank can do it, so can we with the Star Analyzer. And just a DSLR standard. Oh, it was with a refractor, not standalone. Over here is the spectrum profile intensity graph, and you can see what are called the swan bands. This was captured by a guy named Vikrant Agnihotri. He's a nuclear power plant engineer in India, in Rajasthan. In 2013, he was a newcomer. Now, he knows more than I do. I learned from him. And what teacher doesn't like learning from their student? And I do a lot of teaching. I do a lot of coaching and mentoring of newcomers, maybe like some of you will become someday, students in high school. In fact, once you understand a little bit about this, in addition to doing sidewalk star parties or high school outreach star parties, you can go to a science teacher, physics, chemistry, astronomy, and you can volunteer to mentor a student in spectroscopy for a science fair project. And it often wins science fairs. And it's not that hard to do. With your coaching them with your equipment, so as the world opens up during 2021, again, think of that as a possibility because it's nice to have something to offer. So here's a more contemporary example. This is the sodium peak of NEO-WISE. You can see it there, the yellow in the tail. This is done with an objective grading, which I don't keep mentioning because it's important, but just so that you should see the example. That's when you have a grading right on the nose piece here. It's called an objective grading because the light goes through it before it goes through your objective lens. So the light is parallel at that point. So I love this slide. Anybody who uses a C-clamp, that's my kind of observer. Oh, look, I break just about every piece of equipment I work with. So this is really a ding moment here. And that is, if I can find my mallet, I should just go like that, it'd be easier. And that is, you don't have to be an equipment geek to do spectroscopy. Here, Robin Leadbeater, who designed the Star Analyzer, he bolted a video camera to his tracking mount. Now, if it was me, I would have torqued that C-clamp and collapsed that enclosure and destroyed the camera. Thankfully, he didn't. He put a star analyzer right here and he observed the Perseids. And in one frame, he captured a spectrum or there's the image, that's the zero order itself of the meteor right there. And over here is the spectrum. And that gap is this dip right here. And look at the mineral, or not minerals, but the elements he was able to identify here from the spectrum. This is like a weird, like little subspecialty in astronomical amateur spectroscopy. But, you know, whatever floats your boat. Robin does lots of other things too, but there's some people who do this exclusively. So we're not going to talk a lot about the sun spectrum tonight. Just, you'll notice that this yellow line here, in 1868, observing the sun during an eclipse, so it wasn't this big object, because they didn't have a slit back then, they had just a grating. They saw that yellow line, they went, when Bunsen burned stuff on the Earth, he never found anything 10 years ago that was yellow at 58 or 5900. We don't know what it is. So they said, okay, let's give it a name so we can talk about it. The Greek word for sun is helios. Let's call it helium. End of story. Except now we fast forward about 45 years. Two different researchers were studying a particular gas here on Earth. And they burn it to look at the spectrum, and they found a yellow line right here. And they were able to say, eureka, that yellow spectrum for helium on the sun, about which we knew nothing, we've now got it in hand here on the Earth. I love this story because it's such a great example of how science can be done on such distant objects that we aren't touching. So again, this is something that some amateurs do during a total eclipse. They set up a DSLR and they capture spectra, and beautiful spectra too. So with a DSLR, you can also look at novae. Some, for example, have iron absorption lines, others don't. So just a quick review here of Doppler shift. And that is, if a car passes you on the highway and he or she has their horn on the entire time, then you're going to hear something that goes, it's going to sound like this, right? Higher, higher, higher as it's coming towards you, lower, lower, lower as it's moving away, lower when it's moving away, higher when it's coming towards you. That's Doppler shift. Now suppose we wanted to see this triplet spectroscopically. We expected it right there, but when we looked at it, it turns out we saw it shoved over to the right. That would mean that was Doppler shift and that object was moving away from us. It was called redshift because it moved towards the red. But if the object was shifted over to the left, we'd know it was coming towards us from the Doppler blue shift. Let's look at a really cool example. So supernova, exploding star, there's one particular type called a type 1a. It's when two stars are basically, it's a binary star. Or the reason I stumbled there is I realized binary pair would probably mean 4 stars, wouldn't it? So it's a binary system. One of the big stars, the big star dumps some of its gas, somehow it ends up on the white dwarf. And what happens when you pour gas on something hot? You get an explosion. The star destroys itself. Let's look at a real-life example. In M101, there is a supernova. Here is a photograph of the aftermath of a supernova. This is in our galaxy. It's not this one, but it's a type 1a. You can see that it's a sphere, maybe an exploding, expanding sphere. So David Strange captured that spectrum with just, you can see there, a 9-inch SCT, and less than 15 minutes of imaging time, stacked images. And there's the profile graph that he got. Now, you know, we say that we stand on the shoulders of giants in science and so many other things. The giants have figured out that, you know, we already talked about how different types of stars, different temperature stars have different spectra. Different supernova types have different spectra, like fingerprints also. There's another kind of supernova called core collapse when, for example, it runs out of fuel and it just collapses on itself. So now this next slide, it won't be on the final exam, but see this dip here? The professionals have figured out that that dip that occurs down around 6,000 is from silicon for a type 1a supernova. But other core collapse supernovae, like this type 2, it doesn't have that dip. Instead, it seems to have this huge peak in the red. So these fingerprints allow us to tell what type of supernova we're looking at. Is it a pair of stars? Is it a single star, core collapse? Professionals would like our help doing this. This is one of the ways that as amateurs we can help. So Tim Puckett, for example, supernova hunter a few years ago at a conference, he showed this Excel grid with all these supernovae that were waiting for confirmation as to whether that deep ionized silicon dip existed. Is it a type 1a? So that's the good news. The bad news is they're almost always, these days, in galaxies far away from us. So they're fairly dim, so you need a little bit bigger a telescope. But look what David Strange and I did. We measured the wavelength in angstroms of that dip, and we made note of it. Then we looked up online where, if we burnt silicon, suppose Bunsen had burnt beach sand, he would have seen absorption feature at that wavelength, which is different than that one. There's some Doppler shift going on here. I couldn't remember the Doppler shift formula. Wikipedia helped out. When I plugged the numbers in, I was able to calculate with David Strange the blue shift and the speed with which the shell of that supernova was coming towards us. Isn't that amazing? With a backyard telescope. So this is something that you can do. This is not something that you have to be on a mountaintop and be the creme de la creme to do. It's not like those examples in the magazines that we all ooh and ah over. So you may be familiar with this guy. His team did the research before the turn of the century, where they measured the accelerating cosmological expansion. And what type of star do you think that he used as a standard candle? A type 1a supernova. So, well, again, I don't think he used this particular piece of equipment, but I'll tell you, I've got it, if I've still got it here. Oh, it doesn't look like I can lay my hands on it. I had it here a minute ago. You know, when you talk about bang for your buck, he's got $1 million telescope. Yeah, I'm just not going to be able to find it. He's got $1 million, multi-million-dollar telescope, and here we've got $200 of, or you know, a few $100 or $1,000 of telescope. So we're getting a lot of bang for a very little buck. Let's look at the spectrum of a black hole. A black hole, you say, doesn't emit light. How can you have a spectrum? Well, the accretion disk that's spiraling in gets very hot. That matter glows and produces a spectrum. So David Hayworth in Portland, Oregon, south of here, he imaged 3C273. I've never imaged it myself. There's the spectrum. You can see at the tips of those arrowheads on the right, 2 little dots. Let's blow that up. There they are. And let's look at the profile graph. Oh, there's also some peaks here. Well, this guy was 25 years old in the 1960s. And he looked at this and he wanted to figure out what those peaks were. And there's a great transcript of him giving an interview where he describes his experience. It's linked to on my site. You can use the contact form if you can't find it, and I'll send you the link. You know, sometimes in science, the way we study things is we eliminate, we throw away the things that they can't be. In this case, he said, okay, I'm going to go back to square one. I'm going to eliminate these peaks being glowing hydrogen. So this is that screen in my software I asked you to keep in your mind's eye. It doesn't matter that it's vague. The point is that these are the reference lines. This is where we would find hydrogen absorption or emission lines, the Balmer series. But, you know, they don't line up, do they really? I mean, there's nothing up in here, and, you know, there's no big peak here for that. So Martin Schmidt concluded, it's not hydrogen. At least I got something done today, right? Except it was, and he figured it out. These were massively shifted lines. Now, this image was done by an amateur with like an 8 or 9 inch SCT, and not even an expensive camera. This was a modified security camera. So the amazing thing about this is that much redshift allowed us, first of all, we got very close to the published figure, allowed us to calculate using the Hubble constant with just a division. Again, at the time I first saw this, I never had really understood how redshift and the Hubble constant, how they all work. You know, a little bit intuitively. I knew it well enough. once you run the numbers once, do a few divisions and multiplications, it's yours. And I know one of the things in astronomy that we all like is those macrocosmic sort of size and relative enormity of things we observe. Here are two examples from this quasar. First of all, it's 2 billion light years away. We calculated that using the redshift. But if this quasar is as bright that we can see it at that distance, its luminosity must be about 100 times that of all the stars in the Milky Way at the same time. This baby is bright. And here's one more example, which I enjoy, the qualitative approximate examples. If it was as distant as Pollux, all you need to think about is that, as you know, the stars are really far away. If this was where Pollux is, it would be as bright as our sun is. It's bright. It's really bright. What's astonishing and fascinating to me is that this light, even though it's billions of years in coming to us and billions of light years away, still had enough information in it that we could pluck out something that would tell us what it was like back then, back there. It's as if the light didn't age. Now, here on Earth, things age a little differently. Here's Martin Schmidt a few years ago. I've been justly accused of throwing rocks in a glass house. Look, he's got a full head of hair. I'm envious of the guy. Just give it to me, okay? So, two more examples and we're done. So far, we've been looking at features like these, right? And, you know, if we wanted to look at the detail of this hydrogen alpha absorption feature, it would be great if we could just use our mouse wheel and zoom in, like in a photograph of, you know, a grandkid or a friend or a kid. But we can't, and you know that. If you've observed the moon on occasion early on in your observing career, you decided, I want to see that crater bigger, more detail. So you put more magnification in with an eyepiece, and eventually you realize it's not getting any clearer. It's getting bigger, but no clearer. That's empty magnification, and the same thing happens with a mouse roller wheel. In order to look at those details, you really need a slit spectrometer. And here's what that feature looks like with a slit spectrometer. There's lots of other features that just aren't visible here. In fact, we can compare that to the moon. This is the sun reflected off the moon, and look how, as we often do in science, a known thing, the moon not moving towards or away relatively much, compared to Vega, there's an offset there. That's Doppler shift. This object is moving away from us, and we can measure that distance on the x-axis, and we can calculate the radial velocity. It's a very small number. 0.67 angstroms is what we're measuring. We'd never be able to measure that on here, could we? So, you know, my mother always said, and now my wife says, that I should dress for success. My wife tells me this isn't what she meant. But, you know, we're into spectroscopy here. So you can see in the red up there, that's where the hydrogen alpha feature would be. But listen, for those of you watching this at home tonight or sometime in the future, this is 2020. It's been an interesting year, as you know. I'm sure those of you at home here in November of 2020 have had, some of you have had the experience I'm about to describe. And that is, if you look down at the bottom, you know, we're all about color in spectroscopy. You see that those colors go gray. And I can't get, my salon isn't open. And the only salon I've been able to get a hold of, they don't have any appointments. So I'm stuck with that gray. Like I said, you or your spouse or your partner, whoever, probably have encountered some of this, some of you, haven't you? So my last example before we finish up, this gets a little hot, so I'm going to take it off. I have a visual aid. So this is a rotating star. It's rotating very, very fast. This edge is coming towards you, so that light is blue shifted a little bit, and this light is moving away from you, so it's red shifted a little bit. First, let's look at Vega, which doesn't rotate very fast. There's that Vega hydrogen alpha. And here's what I was just saying. The star's rotating, that I'm going to show you in a moment. So this edge is coming towards you, it's blue shifted. This edge is moving away from you, it's red shifted. Let's look at Altair, which rotates really fast. Wow, look how flattened that is. The light that was here Some of it got spread here, some of it got spread there, red shift and blue shift, both. So the giants, these men and women, were just brilliant. They figured out that just by splitting starlight, we could learn so much about the stars without even touching them. So how do you get started? To finish up here, you need a grating. You need almost any kind of camera. You need software. If I was a good salesman, I'd mention, first of all, that I sell the Star Analyzer grating at our site. And secondly, that my software is named RSpec, where the R stands for real time. So it's real-time spectroscopy, because you can do it with a video camera or even a fixed camera under the stars. This is the software I mentioned I had so much trouble with a decade ago. I'm now friends with the authors. In fact, we gave a workshop for the AVSO a couple weeks ago and one in August. The software is really powerful, still a little rough on the edges and steep learning curve. The last thing you might need, see this distance here from the grating to your sensor? Well, it's not critical like focus, but you don't want it too far away or too close. And my site has a little calculator where you plug in your telescope information, and then hopefully you get some green flags here. And if you don't, then you change some things. And a lot of people just use this link and send me a list of their equipment, and I do that for them. And this is a little bit of a speed bump to getting started, but once it's behind you, you're good to go. There are lots of great books out there. And in fact, my site on the links page emphasized some books. The first I list is this one. And the reason I listed, check this out. This is one of the pages from it. So you can see here's helium, here's oxygen. It tells you if you're looking at a ciphered galaxy with a star analyzer and even a webcam, you can do that with a small telescope. You might see these features. Maybe not all of them, but you're going to see some of these features. You'll see, for example, this hydrogen line. So, but the problem is, I'm a knuckle-dragging programmer. I don't know the significance of nitrogen or oxygen. The great thing is that this book also has a whole lot of text. Now, I can't see my video preview now, so I'm not exactly sure how much you'll be able to see. But you can see he actually, in this Walker Atlas, explains to people like you and me, not postdocs in astrophysics, not PhD students, but amateurs. He explains what it's all about. And even if you're not doing spectroscopy, this is a fun book, just as an armchair observer, to read and look at the examples. That's the good news. I normally don't mention this. I was at the doctor the other day. He prescribed some medication for a short while. He didn't tell me what it cost. This is a true story, just 3 days ago. I went to the drugstore to pick it up. It was like $80 for a month. So he was a little bit of a coward, I thought. He didn't want to tell me what it cost. I don't blame him. So this book is sort of the same. This is an $80 book. It's linked to on my site, so you can find it there. And here's something. Many of you know this, that as an affiliate, if I send you to their site with a link and you buy that book there, I make a little money. But, I make about $35 a year on books. I don't even look at the reports anymore. But here's something you might not have known. If you click on a link on my site and you go to Amazon, you don't buy that book, but you buy something else, I make a small commission on that too. So early on when I was looking at the reports, I would see that I made 16 cents on somebody buying a pink My Little Pony. I couldn't figure out how I was getting a commission for that. Anyway, just a little bit of background about how that all works. We've got a great online forum with experts and newcomers. Everybody likes to help everybody. So check that out. It's a great place to read about what people are doing. So about 4 years ago, I gave a hands-on workshop to 100 people in person to the AVSO at the SAS conference in LA. And everybody had sample data that I provided in their laptops. It was an hour-long workshop, and they video recorded the whole thing. It's now on YouTube. My software is free for 30 days. So tomorrow morning, literally, right, it's Monday, you could download the software if you've got the time. You could download the sample data from the same place, and you could play that YouTube video, and in a few hours, you'd be processing spectra. And I guarantee if you do that, you will remember how spectra work and know a lot more than you knew before. So it's a great way to learn. There are opportunities for professional amateur collaboration. these are all amateurs on this line. And then Bob Stencil is at the University of Colorado. He's a professional. They're studying a star, a particular star that I learned about from this. Again, because some of my friends were doing it. It's a type B star. It's a hot star, but it's a BE with a little e star. That E stands for emission lines. Stars don't normally have emission lines. They have absorption lines. This star is thought to have a circumstellar disk that's glowing, and they need amateurs to observe it as it changes. So the AVSO, Stella Kafka is, great executive director, and Arnie before her, professional astronomers. They understand the importance of astronomy and of spectroscopy, which is why they've really stepped up the game at the AVSO. They've got an online database, they've got a forum. So check that out if you're interested. So in the last 200 or 300 years, we've come a long ways, gotten a lot closer to touching the stars or understanding the stars without touching them. And in the last hour, I went a little longer than I'd hoped to. In the last hour, again, we've come a long ways. I hope it didn't feel too much like drinking from a fire hose. I love answering questions. I'd like to thank the club for inviting me tonight. For all those of you who do outreach in normal times, which hopefully in 2021 we'll be returning to, I'd like to thank you especially. Outreach is one of the ways that we pay it forward and backward for the opportunities that we had and took advantage of. And how do we know we took advantage of them? Because we're watching videos like this and giving videos like this. So I'm happy to answer any questions that come up tonight. You can relay them through the moderator of this video. You may see some questions asked on YouTube in the comments section, or you can go to my site and submit a form or even send me a direct email. I'd be happy to hear from you. Thank you all very much. And I'm ready for questions now, so go ahead.
All right. Thank you, Tom, for a great talk. I do invite our viewers online to please put in your questions to our live chat. If you happen to be viewing this at a later time when we are not live, please still add those questions down below. We'll see what we can do to get them answered later. Any questions in our chat? All right. Unfortunately, it seems that some of our people have gotten a little shy.
Not a problem.
So I
Well,
want to thank everyone.
Yeah, I'd like to thank you for inviting me. Go ahead.
Not a problem. And I want to remind everyone, don't forget to hit that follow and subscribe button down below for more great live stream goodness. Also, check us out on our website, UACNJ.org, and our social media through Facebook, Instagram, and Twitter. Like I said, please comment down below if you're watching this after the live stream for any questions you have. Also, any suggestions on topics that you might want to see. And with that, we will wrap up the live stream. And we have a couple people thanking you for very interesting talks. So have a good night, guys.